Hi, my name is Blake Simmons, and I'm the Chief Science and Technology Officer of the Joint Bioenergy Institute, and I'm also the Division Director of Biological Systems and Engineering at Berkeley Lab. And today I'm going to be talking about a topic that's near and dear to my heart, and that is the topic of biofuels and what they can mean for the future of transportation in the United States and beyond, and some of the challenges they face in order to reach their true potential. First, I'd like to talk about the motivation for biofuels and bioenergy writ large. Um, Bioenergy and biofuels have been around for several decades, but they've recently gained increasing importance because of concerns around climate change. And as this map shows, and it's an animation taken of several decades worth of surface temperature plots, you can see that the average surface temperature is rising. And that is not a good thing for humans. It creates a lot of concerns around climate change, around deforestation, and around sustainability of agriculture. And bioenergy and biofuels are one way to combat the greenhouse gas emissions that we currently derive from burning fossil fuels in an ever-increasing way across the globe. Petroleum, of course, is the primary source for transportation fuels and chemicals. And in fact, petroleum, you can say, is ubiquitous in our lives. Everything that we see in every room that we walk in, paint, the floors, the ceilings, are all derived primarily from petroleum. And when we're talking about bioenergy, it's also important to note that it's not sufficient just to replace the fuels. You have to replace everything that we derive from the barrel of oil in its entirety in order to diminish our reliance on it at an enterprise level. So a common theme you'll hear today is that we must move beyond the silver bullet solution and only looking for one particular sector to solve our greenhouse gas emission problems, but rather take a wide range of different technologies and opportunities in order to make a truly significant impact that we need to sustain this planet. We also have a wake-up call for biofuels. As you may have noticed, there have been wild price fluctuations in the marketplace. When every time you go to a gas station, it can be $2.50 to $4 a gallon. And so we can't rely on policy mandates or the assumption that we're going to save the planet by doing the right thing. We have to make biofuels affordable and scalable and viable at the pump. And as you can see, this plot over here on the left is giving you an indicator of about the past 15 years of price fluctuations for gasoline alone. So we can always do what we typically do. And when things are good and gasoline prices are low, we can just burn, baby, burn. I don't necessarily believe in that. I would rather go for a more sustainable outcome. And the one way to view that is to evaluate and consider the true cost of gasoline. It's not just the cost associated with the production of a fuel, but also the true externalities that are associated with it, such as the price associated with adapting to climate change, foreign policy endeavors in terms of military posturing and investments in foreign countries, and again, the true impact on society writ large. And so these price fluctuations do create a big barrier that we have to deal with. And one way to weather that current storm, pun intended, is to focus on the fundamental science and the manufacturing of biofuels and to really create technologies that are affordable and scalable no matter when or where they occur. There has been a global response to biofuels, and there are many nations, as indicated in this map here, that have adopted very aggressive postures and policies to promote the growth of biofuels across the world. Some of the most stringent occur in the state of California, where we have the low carbon fuel standard, which is a very strict policy guideline on how to evaluate renewable fuels to fossil fuels and determine which ones deserve the most credit for displacing the most carbon offsets in the marketplace. The European Union also has a very aggressive posture and policy towards biofuels, and in particular, across the globe, we are seeing increased policy awareness for aviation biofuels in particular, because planes fly across the globe, and where they land and where they take off shouldn't matter in the policy landscape in terms of controlling the carbon emissions associated with the burning of those fuels. The investment in the renewable energy sector has also been relatively stable and growing over a number of years. And this plot here gives you an example of all the different sectors shown here in the bottom of the plot in terms of the technology sector that they represent and the color coding that are in these bars. And then we also have the divided up by sector that you can see driven here in the total number of dollars that are invested in each technology sector. And what I would like to point out, and you'd be very keen to see this in such a small screen, but the biofuel sector represents a very small fraction of the overall investment that is pumping into the renewable energy sector. But overall, the impact that these biofuels is very significant, as shown by this plot here. Conventional biofuels, which are those that are representing things like corn ethanol, also woody biomass that is used for burning, represent by far the greatest contributor to the major sources of renewable energy in terms of energy consumed per year. And then we have these modern biofuels that are the next generation of biofuels I'll be talking about a little bit later on, that are still attracting significant overall interest, but yet have yet to reach their full potential in terms of what they can do in terms of the renewable energy sector. And as one might expect, biomass is a distributed global resource. Plants occur everywhere. Photosynthesis is a worldwide phenomenon, thankfully. And so we have a lot of different types of biomass that are available annually and continually throughout the world. And the real trick or challenge that presents itself is how do you adapt and match the technologies to the feedstock in order to maximize the benefit and the conversion efficiency to maximize the production of biofuels and bioproducts wherever you are in the world and whenever you happen to occupy that world. And so we have a lot of different technology sectors and technology developments that are tailored for a given feedstock in a given area for a given economy. But what would be really desirable is if you could come up with we'll call a feedstock agnostic pretreatment or conversion technology that can be placed anywhere in the world, operating on any given feedstock and operate effectively well and generate an economically viable product. Why that's important is that the biofuel markets are expected to grow significantly over several decades, as this plot shows. No matter what the type of biofuel or what market sector you're going after, be it aviation, be it internal combustion engines, be it diesel, the demand is expected to go up as more and more people inhabit the planet. They want to consume more and more fuels to get them to where they want to go. And we need to be able to meet that demand through renewable and greener alternatives to petroleum in order to keep our hands on and keep control of the greenhouse gas emission problem. Now, when we talk about biofuels, there are several different types. Not all biofuels are created equal. So when you talk about biofuels, it's very important to denote what feedstock it's being derived from and what the final format of that biofuel is. Now, we've been using biomass for a long time, thousands of years, ever since we invented fire. And that's the far left box over there representing the primary combustion and consumption of biomass as a feedstock writ large. We also have first generation biofuels, which is corn ethanol and other starch-based fuels that we've been taking advantage of and using for decades. In fact, the first Model T Ford was designed to run on corn ethanol way back in the early 1900s. The second generation of biofuels are those derived from lignocellulosic biomass feedstocks. And I talked about corn kernels. One example of a lignocellulosic feedstock is corn stover, which is what's left over after you harvest the corn. It's the remainder of the plant that is still available to be converted. And I'm going to be spending most of my talk today on the second generation of biofuels. We also have a third generation of biofuels, which are classified as those that are derived from algae that can produce a whole host of oils that can be converted into a wide range of biofuels and bioproducts. Now, for the second generation of these feedstocks, we have a lot of different biomass conversion routes. There are the biochemical conversion techniques, where we use a pretreatment and enzyme and microbial process to break down the biomass into usable intermediates that can then be converted into biofuels and bioproducts. We also have hydrothermal conversion, which is where we take the plant biomass and we expose it to hydrogen and high temperatures and break it down through catalysis and then upgrade those intermediates into those finished biofuels and bioproducts. And then we have thermochemical conversion, which primarily resides in gasification and pyrolysis to convert that biomass into biofuels and bioproducts. The majority of this talk is going to be focused primarily on biochemical conversion, but it's important to note that all these different conversion technologies have advantages and challenges. But they all have the unique upside in terms of producing biofuels and bioproducts that can displace and replace petroleum-derived products. In terms of the US bioeconomy, it's been estimated that there are 1 billion tons of sustainable biomass that's available every year for any given purpose. And so you may have heard of the Strategic Petroleum Reserve. Well, I would put forward that this 1 billion tons of biomass is our strategic carbon reserve. And the question is not if we should use it, but how we should use it to best impact the economy and our policy initiatives around reducing greenhouse gas emissions. And so if you were to convert that billion tons of biomass, here's what you could do. You could produce about 50 billion gallons that would replace about 25% of the transportation fuels we consume today. You could get 50 billion pounds of polymers and different products that could go into the specialty or commodity chemical market and displace petroleum that way. You could displace about 450 million tons of CO2 from the atmosphere each year, and you could create about 1.1 million direct jobs and keeps about $250 billion in the US economy directly that we currently offsite into other nations to bring in those petroleum-derived products. Well, that's great, isn't it? But we still have a lot of challenges that we have to address before we can meet that promise. First and foremost is that we have to have bioenergy crops that are dedicated for bioenergy. You have to have efficient processes to break those biomass crops down into the intermediates that we need that are suitable for upconversion. One key aspect of that is a pre-treatment technology that basically takes the intact biomass and opens it up and makes it more accessible to deconstruction. Plants and trees and grasses aren't designed by humanity to fall apart currently. That is one of the biggest aspects that we face is the identification of bioenergy crops that are uniquely suited and more efficiently broken down by pre-treatment to make the overall process more affordable. Another key point is enzymes. After you've loosened up the biomass, you have to typically add enzymes in order to depolymerize it into those intermediates. And those enzymes can be very problematic and very costly. And finally, we have a lack of efficient and affordable microbial routes to drop in biofuels and bioproducts. And I'll be talking a lot more about those in the second talk that would follow this one. But in order to set the common baseline here, I want to take a step back and describe what a plant cell wall actually is. Typically, you can view plants and they look pretty simple. You just have to add water, sunlight, and soil and they grow. But these are very robust and hierarchical structures that are composed of many different elements to really create a self-reinforcing structure that can tolerate wind, rain, pests, extreme fluctuations in temperature, and the occasional knock of a human walking down the street. So the three primary components that I want to highlight are hemicellulose, cellulose, and lignin. Cellulose is the primary constituent of biomass for calcitrants. It's also the cotton fiber that we use in shirts. Thankfully, cellulose is very hard to break down because obviously when you put a cotton shirt into the washer, you don't want it to melt. Cellulose starts off in very small structures that are molecularly determined to the C6 ring that is made by the plant cell wall. That gets assembled and elongated into fibrils that very tightly pack as they are made, and they create a microcrystalline substrate that is very, very hard to break down. In addition to cellulose, we have another sugar-containing polymer, hemicellulose, which is basically everything that is a C5 sugar. Everything that's not a C6 we define typically as hemicellulose. And whereas cellulose is a really homogeneous structure, hemicellulose can be very complex and very varied, even plant to plant, that are grown on different acres. Because the plant adapts to the soil environment, it adapts to the weather environment, and so the things it expresses are very highly tuned as a function of that. Finally, we have lignin, which is a hydrophobic polymer that contains highly aromatic residues that gives the plant some very unique abilities in terms of water transport, nutrient transport, and resistance to disease and infection. Lignin is commonly associated as your anti-biofuel. There are a couple of adages out there that describe lignin. One of them is that you can make anything out of lignin but money. But I'm here to tell you that you must do something beneficial to lignin in order to realize the true potential of these plants as a source of biofuels and bioproducts. The three components taken together represent typically about 90% of the dry weight of the plant cell wall. And so if we're talking about maximizing the carbon conversion efficiency, we're really talking about developing technologies that can break down and derive biofuels and bioproducts from all three: cellulose, hemicellulose, and lignin. And another way to view this is how they actually exist out in the environment. And this picture over here is taken from a scanning electron microscope image of a plant cell wall that has been dried. The holes in the biomass are where you would typically find the plant cell in normally viable growing plant tissue. What remains are these secondary cell walls that have all of the carbon that we're trying to access and liberate and turn into biofuels and bioproducts. Now, those secondary cell walls may look simple in that former picture, but in actuality, they are that complex hierarchy of different structures and different chemistries that create a very hard to break down structure, which is good if you're a redwood tree and you want to be around for 1,000 years, but not so good if you're a human trying to convert that redwood tree into something very efficiently into biofuels and bioproducts. And at the core of it is, again, those three plant components: cellulose, hemicellulose, and lignin. The lignin is represented by these blue circles here on the outside, decorating the complex composite material, if you will, of cellulose and hemicellulose. And the reason why lignin is on the outside of the plant cell wall is that the plants have evolved very intricate ways to transport water from the root system in the soil, where the water is, up into the branches where it's needed. And so, in simple terms, lignin is important, an example for water transport. When you take a stalk of celery and you stick it into some material, and like a colored dye, and you see the colored dye go up the stalk of the celery, lignin acts in much the same way in creating that hydrophobic induced water transport mechanism from the root and soil up into the higher parts of the plant. And then again, at the core of it, as you see over here, is a cellulose microfibril, and how it is tightly compacted into very rigid structures that give the plant the primary resistance and rigidity that you encounter across the globe. Now, in addition to all these different mechanistic ways and direct visualization ways to understand the plant cell wall, what is really necessary and developed recently is a computer model of the plant cell wall, where we can understand all of the different bonding mechanisms that take place and develop a fundamental understanding that enables us to more efficiently develop pretreatment and conversion technologies that can break all those constituents down into the intermediates that we want. And so here is a plant cell wall model that was developed on a high-performance computing engine in Oak Ridge National Laboratory. The hemicellulose are these green bundles that are outside of the cellulose microfibrils that you see here in blue. And then the lignin is the red pendants and blobs that you see in complementation to the hemicellulose that form the overall structure of the plant cell wall. So now that we have computer models such as this, we can put these models in, put different chemicals, solvents, microbes, and enzymes, and understand how they all interact and change the plant cell wall, and how we can develop more efficient ways of breaking it down. In addition, now in the modern era of genomics, we have the ability to tailor the composition of these plant cell walls so that they're uniquely tuned to more efficiently break down as a function of exposure to chemicals, enzymes, and microbes. So some of the key challenges in converting lignocellulosic biomass to fuels, you can see here hemicellulose in yellow, lignin in red, and cellulose in blue. Cellulose, most of biology, like us, uses glucose as a major energy source. Lots of microbes like glucose as well, and that is what is produced when you break down cellulose into that targeted intermediate. So we would like jelly roll plants. We would like more cellulose that would enrich for glucose that we could then more efficiently break down and convert into biofuels and bioproducts. The complementary argument there is that we want less hemicellulose. If we can really dial up the cellulose content and dial down the hemicellulose content and maintain the overall viability of the plant, that would be a very good thing in terms of overall conversion efficiency. And then finally, we want to make that very recalcitrant lignin easier to break down. And there are several ways we can do that through genetic engineering, as well as marker-assisted breeding for plants, such as looking for lignin types that have a lower molecular weight or are more easily cleaved by more benign environmental conditions. In terms of the pretreatment process, right, I spoke to that earlier. That is a process by which you take these intact biomass and you loosen them up. And the primary goal is to take the lignin and get it out of the way of your conversion process. So a typical pretreatment is one that would take the biomass, it would solubilize the lignin and then shunt it away to be dealt with later. And then what you produce are these sugar-containing polymers, cellulose and hemicellulose, that you can then uniquely tune and convert into your targeted intermediates such as sugars. And then in terms of the microbes, once you have all these sugars that we produce, you have to have efficient microbes to convert those into biofuels and bioproducts. Now, one of the big problems is that the pretreatment step that you use to convert the biomass initially can generate inhibitors that are toxic to these microbes. And so what you want is fewer inhibitors generated by the pretreatment process in order to make the microbes more viable and healthy and able to convert more sugar into these biofuels and bioproducts. And in addition to the microbes better, we also need enzymes that are better at the process that can also tolerate those inhibitors. Because what you don't want to do is generate a poison upstream that really negatively impacts your overall conversion efficiency downstream. And then another added aspect, as if it isn't complex enough, is that these enzymes that we use are very expensive. They can typically add about 30 cents to $1 per gallon of fuel produced currently. And so we need either more efficient enzymes, less enzymes per unit of mass for the biomass, or something that is much faster and better than these enzymes to generate these sugars. Because at the end of the day, this is a sugar platform technology. We want the sugars at high yields in order to convert those into biofuels and bioproducts. And just to give you an idea of the overall metrics that we typically associate with a make or break point, is that we want to achieve about 90 to 95% yields of all the sugars that are initially intact in cellulose and hemicellulose and converting them into their monomers. Now, once you have the sugars, it's now what should we produce? As I mentioned earlier, ethanol is the primary biofuel that you can encounter today. In fact, when you pull up to a service station pretty much anywhere in the United States, it's typically blended in at 10% levels for all gasoline. And the current production of ethanol is currently capped at 15 billion gallons a year from corn. But you can see that we have all these different types of biofuels that you can produce. And one of the reasons why we want to produce them is that there are some drawbacks to ethanol. You can't blend it up to 90% levels and make it run very efficiently in a lot of current engines. So what you'd ideally like to do is get some higher molecular weight alcohols that have lower miscibility with water, right? Ethanol, as you probably, if you're over 21, you probably enjoy alcohol in blending with water. That's a beer, a wine, a gin and tonic. Ethanol is freely miscible with water. But if you're dealing with a fuel that isn't so kind to humans, that's toxic to humans, in fact, that's freely miscible with water, if you had a spill of that in any high-density population area or in any watershed, that could be a significant environmental and human health consequence. So what you want is these higher alcohols that have lower miscibility with water. They have higher octane numbers equivocal to gasoline. And you want them to be volatile because obviously you're not burning liquids into your combustion engine. You're actually taking vaporized mist of them and burning those. Another alternative is alkanes. You could look at diesel or gasoline replacements. You could look at esters. That's just classic compounds here. And those double bonds are the ester bonds that you find. Those are typically seen as diesel replacements that have appropriate cetane numbers. And then you can look at cyclic alkanes and alkenes that are jet fuel replacements. It's important to note growing trends in the transportation sector. One is that we have increasing electrification and increasing hybrids and increasing alternatives to gasoline for the internal combustion engine. So it is expected that the market for the internal combustion engine fuels will drop significantly. However, the markets for diesel and for planes is expected to grow in the United States. And so if you're really making a bet on the future and what fuels you should produce, odds are that it would be in your favor to go after a diesel blend stock or an aviation blend stock. Now, when we talk these advanced biofuels, you'll commonly hear them referred to as drop-in biofuels. And that is because they have a high molecular identity in the chemistry to the hydrocarbon fuels that we derive from petroleum. And so the thought is that they could be blended at very high levels into any point of the transportation or distribution chain and then burned in the engines without any negative impact. And in fact, some of these fuels we call performance advantaged in that they have a higher energy density or different branching mechanisms that you can get from a petroleum-based fuel, and they actually enable higher engine performance. And I'll get into that a little bit later. And then finally, for ethanol, it's a great place to start, but we may not want to end up there. And at JBEI, we have a mantra that basically says ethanol is for drinking and not for driving. And we don't do any work on ethanol-based fuels at the Joint Bioenergy Institute currently. Another great opportunity space, and something that's really exciting for us, is the co-evolution of biofuels and engines. We have a wide range of different combustion environments that translate to different powertrains and different vehicle models. And the idea being, what if you could design an engine environment that operates very well on a fuel mix that is fit for purpose. And so, typically throughout energy and transportation sectors, you just take what you can pull out of the ground, you crack it and you convert it, you clean it up, and then you throw it over the wall and say, burn it. There has been very little dialogue typically between, we'll say, the energy producers and the OEMs for auto manufacturers. But now we have this unprecedented design space where we can take a look at those different molecules and understand how they perform in a function of these different combustion environments. And so now we have the opportunity to not only reduce greenhouse gas emissions by creating a sustainable fuel that's derived from a plant instead of petroleum, but now we can increase range of the vehicles, and we can get more bang for the buck, if you will, and be able to enable vehicles that go farther than they can on a petroleum-based fuel. And so you get a double benefit. You get greenhouse gas emission reduction by virtue of deriving the fuel from the plant, and then you use less of that fuel on a per kilogram basis in the combustion environment to move the vehicle forward. And there's also another element here of, maybe you could come up with a BioAdvantage fuel that actually enhances performance across any different vehicle type. And that would create what we think a different market pull or consumer pull and the desired output and desired need for these fuels in these cars, because people will want to use them because they make their cars better. And so again, to move into the end part of this talk, we're not only talking about fuels. At an enterprise level, we need to replace the whole barrel of oil. And so this top line shows you how we go from feedstocks to fuels. We go from pre-treatment to enzymes to microbes. And then what about lignin? We talked about lignin for a good spell. Well, what do we do with that? If we can make anything out of it but money? Well, the good news is that there's a lot of rich chemistry in this lignin that you don't want to throw away. Currently, most biorefineries take that lignin and they burn it for waste heat to drive the plant operations, which is not a good use of that very rich carbon. What we'd like to do is similar to breaking down these polymers composed of sugar into these monomeric sugars. We want to take that lignin and break it down into these monomeric and aromatics. Aromatics are a very important part of aviation fuels. They keep the seals in the engines swollen so that the airframe engines don't malfunction and fall from the sky. That's an ungood outcome in engineering parlance. What we can also do is take all these sugars and these aromatics, and we can develop other microbes that will convert them into polymers, be it the commodity polyethylene, polyethylene terephthalate, polyesters, polycarbonates, that go into all of these, I got to back up here, into paints, into these polymers, into these different commodity products that really allow us to get after replacing the whole barrel of oil, which at the end of the day is really what this is all about. We're trying to take the onus off of the drilling operations and put the onus on the agricultural sector to power our future. That is the end goal, because that is the only way we're going to significantly reduce carbon emissions on a global level by any consideration. And then just another important point to underscore this, we really have to make them affordable and sustainable. We can't come up with a gold-plated solution that nobody can afford. Nobody will adopt it, and we won't get to the end game. So in summary, I just want to finish on some of the advantages of these biofuels, hopefully, if they're done right. And it's important to note that some biofuels are done wrong. Palm oil biodiesel is a great example of a biofuel that isn't renewable or sustainable. And nobody in the biofuels industry really wants to save the planet by destroying it. So we have to make them renewable, we have to make them sustainable. They can significantly reduce greenhouse gas emissions. They can be sourced from a wide range of starting materials across the globe, and they can be tailored for any given combustion environment. And that's another performance desired attribute that is really exciting to contemplate and what it could really mean, especially for the aviation sector, where if you can make a fuel that allows 10% enhanced range on an airframe, that would be a significant game changer. And then it also has the ability to stimulate local economies in rural areas. And that is another key point. Corn ethanol and the explosion of that sector in the Midwest really generated a lot of income and economic opportunities in these rural areas that are looking for economic promise and some kind of advantage. And again, these are not easy. There are a lot of challenges in biofuels that we have to address. Again, that a current lack of scalable and sustainable bioenergy crops, although there are a lot of strong candidates out there like switchgrass and sorghum, There are difficulty in deconstructing and separating these bioenergy crops into targeted intermediates. Those are those sugars and the aromatics that we talked about. In order to do that, we need to have a robust pre-treatment technology that you would really want to be feedstock agnostic. You'd like it to be able to take any biomass feedstock and efficiently break it down no matter where or when in the world you are. You also want to make these enzymes much cheaper or require the use of a lot less of them. And then finally, a lack of efficient and affordable microbial routes to drop in biofuels and bioproducts. Although I will say that across the board here, there have been significant advances in the past 10 years that are already seeing marketplace penetration as we speak. With that, I'd like to thank you for your time. I'd also like to thank everyone at the Joint Bioenergy Institute for making a difference in biofuels. I'd also like to acknowledge the Department of Energy for funding. And thank you once again for your time, and have a good day.